We are live now. So, hello and namaste again to everyone. Welcome to the session 7th of Online Space Workshop 2020. I'm Saurabh Pauril, your host for today's session. For this session, so today with me I have Julian Fernandaz as a speaker and Jiten and Rakesh Chandra Prajapati as our participant. Julian is currently co-founder and CEO of FOSA System. He has also developed and launched a Pocket Cube, FOSA-Sat-1, and he will be launching 2 more satellites this year. So he'll be presenting about the data from the first IoT Pico satellite in space, that's his satellite FOSA-Sat-1. Please share your queries in the comment section in the YouTube channel so that we can forward your question to Julian. So now I'd like to request Julian to take over the session. So here to you, Julian.
Thank you very much for the great introduction. I hope you can hear me fine. So I'm just going to go straight into it then and start explaining for myself what this whole project is about. So I'm sure some of you have heard about FOSSA-SAT-1. We launched it in December of 2019 aboard an Electron from Rocket Labs. And since then, we've been operating for a couple of months. We've got quite a bit of data off of it. And in this presentation, I'm just going to go over the basic idea we had with the satellite, the manufacturing, the testing, and finally, the data we have, as well as what we're doing for our next missions. So starting from the very, very start of this whole project, I just wanted to make a mention to how FOSSA Systems sort of started. So this image you can see here on the left is a small femto satellite, in part inspired by Zach Manchester's little kicksats, which I made, I think now must have been 2 or 3 years ago when I was first starting in the Pico satellite world. So it had a little barometric sensor, an IMU, a magnetometer, and a transmitter. So just our first dive into the satellite world that really got us interested in space. And based off of this project, I started a thread on Reddit, and this just goes to show how easy it is to start a project online nowadays without any funds. We started this online thread on Reddit and immediately started working on something a bit more serious, trying to actually get to space. And with this, we created an international team of engineers from a bit all over the world. So, I'm based in Madrid, Spain. This is where our manufacturing and testing facilities are, and where we carry out most of our activities. And then we have members from Czech Republic. Jan Groms, our lead software engineer, is in the Czech Republic. Richard Bamford is in the UK. Ulrich Prince, Peter Butchiger. We're a bit all over the world, mainly in Europe, with regards to the people collaborating on this project. And so you've probably heard about this several times now regarding pocket cubes and why we've went on to using this smaller form factor in order to have reduced launch costs and reduced development times and cheaper launch costs. So I'm not going to explain this too much. However, obviously, with the revolution of the CubeSats within the nanosatellite context, we've been able to really democratize access to space and reduce the costs involved in getting experiments into low Earth orbit. And pocket cubes is the next step to this revolution, getting it down to sort of the cost of a car for 25,000 euros, with orbital being able to get into space. And as you can see, this is just a very basic graph regarding the trend for nano satellites. It's a bit out of date now, where we're in 2020, but as you can see, it's a very fast growing market. We've got people from all over the world getting into space. And most importantly, we're not only getting academia getting experiments into space, we're also getting companies which are starting to give real tangible services from space, which are contributing towards telecommunications, Earth observation, and in general just the development of the satellite industry, being able to compete with larger players which have been in the market for years, like Hispasat or Boeing, or any other large company which has been launching huge satellites into space for dozens of years. And once again, just repeating myself with what I said before, the main points which made us use Pico satellites was a reduced launch price, a reduced development and design costs, and just a general lower barrier to entry. As students getting into this project, when I first started, I was 15 years old. It wasn't it wasn't a viable idea to spend 100 or 200K on a CubeSat project. So that's why we had to go for the reduced Poker Cube form factor, which also has its disadvantages, but we concluded that its advantages were much better. So regarding the mission of FOSSASat-1, when we first decided to come up with this project, we had some clear objectives in mind. Obviously, the first being demonstrating a Pico satellite in space for reduced cost, and demonstrating a completely COTS architecture with which anyone would be able to easily replicate, hence the use of our processor, which I'll explain a bit later, and how we link to the Arduino ecosystem. But our payload was actually a LoRa transceiver. The idea with this is creating an Internet of Things network, which people would have been able to connect to carry out any sorts of transmissions and reception of messages all over the world. So LoRa is something which, at the time when we first came up with the project, wasn't actually widely used, not even in terrestrial applications, let alone in space. Now we've got companies like Lacuna Space, which are starting to give services. However, when this first was conceived, it was very new. No one had really thought about LoRa for satellites, or at least launched an amateur LoRa satellite. FOSSASat was a first in that regards. And then we have an educational objective. Fossa Systems is a non-profit association in its foundation. So we have very clear goals with regards to how we work as an open source project, and how we want to get the project to educate people from all over the world in that sort of outreach perspective. So once again, LoRa was chosen due to its ease of use, really. Thanks to LoRa, we're able to, first of all, have a very basic transceiver on the spacecraft. They're ready-made units which we don't need to develop. But most importantly, on the ground, we're able to get ground stations for a very reduced price and using very reduced antennas with regards to their gain, such as a simple wire, just a copper wire. The link budget works out using under 100 milliwatts, and even inside the ISM bands. And we're able to communicate with the satellite using $3, €3 worth of equipment. And that was very important for us, since we wanted to have everyone access this satellite. And then besides from that, obviously we have a very, very robust and high link budget, which allows us to use reduced power on the satellite itself, and that aligned with our low power goals due to the reduced surface area on the satellite. So here's one of the first sketches of FOSSASat-1. You'll notice some of the things have changed compared to the final model. However, it's fairly close. As you can see, we've got the 1P 5 centimeter sided form factor. We've got a UHF dipole. Our carrier frequency was 436,7 megahertz. And then one important thing about our satellite are these deployable arrays. So FOSSASat-1 was the smallest satellite ever to have deployable arrays launched into space. Unfortunately, we'll go a bit over how these failed in the mission. But in theory, it was our way of getting more energy in space to be able to have continuous operation throughout our orbit for this Internet of Things use. And then internally, we can see the common center stack, aluminum frames externally, and most of the satellite is made from FR4 1.6 millimeter PCBs. So one thing I'm going to go over now is the iterative design of FOSSASat-1. Here we've got the first design we made, which was around September of 2018. So now quite a long time ago when we look at it. As you can see, it's quite different to what we have now. We've got 3D printed parts. It was just a bit of a viability study. And the idea with this was to experiment with the technology, hands-on, and avoid having to sit at a computer for a full year researching and getting stuff done perfectly. We wanted to experiment with technology for ourselves and actually touch things and see that things are working. One thing is a data sheet, and one thing is how the satellite behaves in real life. Unfortunately, data sheets are very misleading, and I'll go over that a bit later on with our electrical testing. But generally, this was the idea, an iterative design which would allow us to touch the satellite from the beginning. And this serves two purposes. The first is obviously getting to touch and work with the hardware in real life, which is what I just mentioned, is very important. And the second is having a tangible product which we're able to show off to different possible investors, and to be able to get the mission off the ground with actual support. One thing is a render, and one thing is an actual working satellite. Even if it's just an MVP, a prototype, which you can show people at conferences. And that's actually how we got funding for this project, just showing these little Pico satellites at conferences and explaining our work. And so here's his second iteration. Main thing, obviously, change of colors and PCBs, but that's not something too important. And here we have the last satellite. So this is actually the flight model. As you can see, it's absolutely covered in solar panels. In total, we have 100 cells for the whole satellite. And the differences with the first MVPs being obviously the hinges were redesigned. We had new solar panels. The electrical architecture was redesigned. We can see here some springs for separation, and a couple other minor changes, but we still maintain our initial ideas of having solar panels go up 135 degrees from the satellite. So trying to make it as symmetrical as possible, considering that we don't have any sort of active control and determination systems. And now onto electronics. As you can see, our first design had a redundant dual 80MeG328P system, and we had an SX1278 transceiver. And we had a couple other bits and bobs inspired of other satellites to be able to deal with, for example, single event latch ups, single event upsets. We have Watchdog. We have a TPS2553 current limiting and current latching devices, which allows us to deal with these radiation-related problems. We have temperature sensors, we have current sensors, we have MOSFETs for separation, and we also had considered other options such as external FRAM to be able to have a backup with regards to the Arduino's memory. And in the end, we decided to go for just using the EPP-ROM. So the design mentality was always, KISS with the whole project. It was keep it stupid simple. We wanted to avoid adding extra components and just rely on single points of failures. We didn't want to have, additional points of failures in the project. And in part, that actually worked pretty well for the mission and allowed us to avoid lots of problems. Back to what I was saying regarding the EPP-ROM, what we finally did was simply a cross-check within several sectors of the memory and basic correction algorithms, which would detect when we have any sort of issues caused by bit flips within our memory. And now regarding the mechanical structure, we really decided not to complicate ourselves. We have two basic aluminum 6061 structures in anodized black. And we're using brass standoffs to sort of get a bit of that load off our PCBs. And that helps with axial and lateral loads in both directions. And then the internal stack is held with M2 bolts. And we have a total of around 5 PCBs. The bottom two being our MPPT system and our OBC. And now back to the solar panels. This is, I think, one of the most important parts of the Pico satellite. So power generation is very important in a Pico satellite. It's really, you cannot go wrong. If you have any sort of problems with the solar panels or your MPPT system, your whole mission is going to die. And in this aspect, this is something quite complicated, especially when you're making your own solar panels. It's quite a big hurdle, trying to make your own solar panels, especially due to the time it takes. So as you can see, we had something like 233 cells, which we had to solder together, and these panels are double-sided. So this involves, placing your solder paste very carefully, and having to use a a little vacuum tool to place your solar panels individually. Then you have to evenly heat them, solder them, flip them, do the other side. We decided to use an acrylic conformal coating on the panels to avoid any sort of degradation, and most importantly to avoid our inner panels getting damaged from the antenna once it flips up. And that was also very complicated. You know, we had to put it in the vacuum chamber to get all the bubbles out. And once the solar panels were done, if we had any sort of issues, we had to use solvent to get the epoxy off. It was quite a complicated process. In total, it took us around 2 weeks of several hours per day. And one very big problem we had was with the solar panel manufacturer. The solar cell manufacturer, which is Trisol X. So these solar cells are actually some cutoffs sold by this company now, this German company, I forget the name, by Azospace. So they sell these large cells, and the cutoffs are being sold at a reduced price. And Trisol X is just a reseller. The problem we had with Trisol X is, as you can see, these cells are actually cut to a custom dimension. They're not the typical Trisol X dimension. These are laser cuts to be able to fit better into the 50 millimeter panels. So this actually maximizes our surface area quite a bit. The problem is Trisol X cut them the wrong way around. And then in the datasheet, they flipped the anode and the cathode. So this delayed us a couple of weeks, and it had to make us redesign our diode system and our MPPT system. It was a really big pain, to be honest. And we've decided not to use Trisol X for any other projects. Now we're going only for Azospace and IXYS cells, which you'll see on our next iteration of satellites. And regarding the attitude control of the satellite, we obviously didn't have any space or power to be able to use an active attitude control system, besides not having the knowledge necessary for designing one, which is quite complex. So we decided to go for a passive system using 2 permanent magnets and hysteresis material. And the idea behind this is the satellite acts like a compass, turning around the Earth, and aligning itself with the electromagnetic field of the Earth. And in this case, we had it such that the antenna would be pointing with its maximum gain at Spain when it was over Spain. And now some closer pictures of the final flight model, electronics. As we can see here, we changed some of the components, but we're back with the ATmega328P Arduino microprocessor, and we decided to use this since it was very common. Well, it is very common. It's used by millions of people all around the world, and it's a very easy to replicate setup where students from anywhere in the world can experiment with it and be able to program with the Arduino ecosystem. So it's quite limited with regards to its use and its memory, and we're not using it anymore. But for a first mission where we're doing very basic data handling with just messages and a couple of sensors, it's more than enough for the project. And I think in the final compilation of the code, we had something like 500 bytes left on the memory of the processor. So it was just enough to get the mission done. And now here just some other pictures in the clean room of all the electronics as we were getting them done. We actually made 2 flight models for everything. So we had 2 Phosphosat-1 flight models. The idea being that we'd be able to swap them out if we had any sort of issues at any stages of testing or just before integration. And this is another quite funny slide. Initially, we were manufacturing it really in-house. So this is the next definition of an in-house manufacturing procedure. A lot of manufacturers say, yeah, we do in-house. We have our own facilities. This is my workbench at home. And as you can see, I've got very janky DIY setup with PSUs and oscilloscopes off eBay. It was really on a shoestring budget initially. Obviously, it's changed now, and we're working in actual facilities. But 2 years ago, when we started off with the project, we were working with this, and it just goes to show that you really don't need thousands of euros to be able to develop a Pico satellite. And at this stage, I think the full Fossilsat-1 project had cost maybe under $1,000, mainly in PCBs and electronics of Mouser. And now here's a bit more final facilities. We were in an ISO 7 clean room at our local university. And then we had access to other facilities around Madrid, such as a donated laboratory with an evaporator, which we were using to do vacuum tests on the satellite for deployment. And with Tesla coils and with a bunch of other cool stuff. I have to say I had quite a fun time at this laboratory. We even had an electronic microscope, nothing to do with satellites, but it was a fun experience. And this is the final setup. These are the two workbenches where we made the whole Fossilsat-1. So this is the ISO 7 clean room at the university. We had we were following standard ECSS procedures with regards to using, proper lighting, proper grounding, using proper safety procedures, and all the soldering was carried out inside the clean room using a fume extractor. So we decided to really keep it very clean on Fossilsat-1. It's a bit overkill. It's really not necessary. You could probably get away with making all the electronics outside and then doing the final assembly inside the clean room once you've cleaned everything. But either way, we decided to make it, to make the satellite that way, and it worked out fine. And so here's the final satellite, weighing 231.4 grams. It's on the heavy side. So the limit is 250 grams, and we decided to go as heavy as possible, especially considering that we're in a very low Earth orbit. We're at around 360 kilometers when we get deployed. And this means we have a very reduced lifetime, and any extra gram is gonna allow us to live for a couple days extra. And in this case, we're 20 grams from the limit, and this allows us to live for around 6 to 7 months. Here's a picture during assembly. Our first satellite, obviously, it wasn't very well optimized. As you can see, we've got here the PTFE cabling. Obviously, we can't use silicon cabling. It's these little details which really make the difference when you're making a satellite, being careful with the solder you're using, with the epoxies you're using, with the cables you're using for outgassing. As you can see, it's quite complex. So assembling the satellite took around 8 hours and soldering everything up together. And then for any sort of testing, it was very complicated to get in there and do anything. So definitely we've had a full redesign and a change on the mentality of making this satellite. But we've learned so much from Fossilsat-1. It's really opened our eyes to the Pico satellite world. And I think there's no better way to learn about satellites than actually launching a first one into space and getting a first-hand experience, not only on the hardware-related aspect, but also regarding legislation, paperwork, everything you need to get done. There's no way to learn about it but doing it yourself for the first time. And now getting a bit more technical with regards to our RF setup, I'm not going to go over the exact specifications, but we're using LoRa for uplink and downlink, GFSK for uplink. The IRU required us to have a backup modulation in case LoRa failed. The IRU were very skeptical with regards to LoRa, and in fact, it was very close to us not being able to launch due to the fact that they were arguing that it was a proprietary modulation which can't be decoded by amateurs, which in the end is not exactly true, since we're able to get receivers for $3 on eBay. And then RTTY. This is very important. I'm going to explain how RTTY really saved our mission later on. But it goes to show how keeping with some legacy modulation can really save your mission. And regarding functionality, the satellite is a repeater for amateur messages in various LoRa configurations. So you were able to change, spreading factor, coding rate, and all that good stuff. And then you could request different packets in different LoRa configurations, and you could request satellite info on sensors. So we try to make it as versatile as possible in case something didn't work. We weren't very sure how LoRa was gonna behave itself in space, so we decided to leave margin and be able to change all of our software-related parameters from the ground using commands. And with regards to the link budget, we had around 158 dBs. We could have an uplink and a downlink using ISM 10 milliwatts. So it's quite amazing. And we actually demonstrated this in a practical manner, which we'll explain later on. And we're just using a very simple tape measure dipole without a balun, using a direct connection to a UFL cable into the transceiver. And now regarding LoRa from Leo, this is a bit outdated now, especially because there's a lot of information, and this isn't so critical. But when we first developed FOSSAT1, it was very important to carry out certain investigations regarding LoRa. So LoRa has two tolerances to Doppler. The first is the total tolerated drift, which the satellite can handle when you're transmitting or receiving from it. And that's very easy to test, just changing the frequency of on one of the transceivers and trying to establish a communications link. That's really not a complication. In the case of LoRa, it's 20% of the bandwidth, and at 125 kilohertz, that gives us more than enough margin for the plus minus 10 kilohertz we encounter in space. And then the big problem we encounter is the tolerated drift per symbol. So within a symbol, the LoRa modulation can only handle set drift in hertz. And as you can see here, the Doppler rate or the shift per second of hertz, the deviation increases as your pass reaches its top point. And using a spreading factor of 12, this actually meant that we had some offline time during the pass. So here's just a basic graph. We can see how at around 45 degrees, we would be losing the top 15 seconds of the pass. That's why we decided to go with a spreading factor of 12, which completely eliminated this this problem. And any other spreading factor below 11 will not have this problem. So this concludes the viability study with regards to Doppler, and we'll soon be publishing a full document regarding the FOSSAT1 mission, where we explain all the formulas involved in calculating that, and all the results from the FOSSAT1 mission, in a written form. So this is our final configuration. We're reaching 335 bytes per second, and then for GFSK, we're using 1.2 kilobytes per second. And then we also have a drift due to the crystal. That's why we decided to go for the SX1268T, which has an integrated TCXO. So without this TCXO, it's practically impossible to establish a link with the satellites, since you get a drift which adds on to the Doppler and in general can give you quite a bit of problems. And now just a bit of a fun experiment regarding the maximum range of LoRa. This is a dumb, simple calculation, but it just goes to show, how you could establish a link to GEO using very simple antennas at 18 bits per second, which is just quite curious. Obviously, we're not reaching these distances in LEO, but it goes to show, the possibilities which we have with LoRa and with going down to very low data rates. And now testing, this is very important in a satellite. As I said, datasheets lie, hardware lies. Nothing is the same as theory. So it's very important to, to test stuff in a practical manner. And we can just see here how we were testing the antenna on a VNA using Rohde-Schwarz VNA and a spectrum analyzer, trying to see, how the transceiver is actually behaving itself. And in the end, with the setup, we were able to reach a VSWR around 1.02, which is quite good for a tape measure antenna. And once again, field testing in a practical manner. Here you can see us launching a weather balloon with a dummy satellite payload, and then being able to receive using a wire antenna. It's quite amazing. We were able to reach distances of around 500 kilometers using 25 milliwatts. And this really just gave us a practical justification that our system was working and that it was going to be able to establish a link from low Earth orbit. And keep in mind, this is SF7. So SF11 is going to give us a much better performance. And in general, this is also a very good educational activities to carry out with schools and, just get a hands-on experience with satellites when you're enabled to launch one into space. And solar panel testing also very important. Here you can see the sun simulator at the university, getting some testing done on all the individual panels. And thanks to this, we were able to determine a couple of failures which we had on specific solder joints with the panels. And I think a sun simulator is a very important tool. In fact, I just built one a couple of days ago to be able to test panels at home. With the COVID situation, I don't have access to university, so I built my own LED sun simulator, and that's very important for making sure that everything's working properly. And now more testing with regards to Phosphosat 1 MPPT system. Here you can just see our system in the clean room, where we had our battery temperature sensor, an IMAX B6 charger, which was able to characterize exactly what the capacity of the battery is. We're using an NP BX1 Sony battery from a camera, and in fact it was quite close to the vendor's capacity, so we were quite happy with that. And just with a set of multimeters characterizing the efficiency of the MPPT setup, and using these SPV 1040s, we're able to get around a 95%, 96% efficiency, which is quite good. And then we're using just a simple LDO regulator. Since we're stepping down from 3.9 to 3.3 volts, we thought it wasn't justifiable to use a switching regulator, since that could possibly introduce some noise into our signal if the regulator wasn't properly designed. And LoRa chips are very, very susceptible to noise. In fact, if you run, for example, a LoRa chip on a USB battery bank, so using those 5 volts, the standard cheap Chinese battery banks reduce your link budget at around 50%, just from the noise introduced from the switching regulator. And we decided not to risk it, just use an LDA and keep it dead simple. And now the actual practical testing regarding the mechanical aspects of the satellite. This is very fun. I love showing this video if it works. Let me just go back. Okay, so that's the satellite being shaken up to 2000 hertz. It's quite hard on the satellite, but with such a little mass, it's not a big issue. And you can see here the aluminum cage which we made for the 1P satellite. So here's the cage, and the satellite the cage can move in different axes, so we don't have to use the table, and we can do all the testing in around 2 hours. It's a very fast setup, and it allows us to test a 1P satellite in a very limited time. And this was carried out in the Catalonian Polytechnic University inside an ISO 7 clean room. We also had a TVAC there, but we ended up not using it since we had our own facilities. So this is the TVAC we had at our own laboratory. Unfortunately, it's only an ambient to hot TVAC, but that was enough to be able to carry out the obligatory bake out of the satellite. We need to bake out the satellite to make sure that all gases have been expelled from any surfaces, and then to be able to see that it complies with the total mass loss restriction. So the satellite can't lose more than 1% of its mass. And as you can see, the setup is literally a halogen lamp hitting an evaporator, which was down to 10 to the minus 7 millibars. And we had a set of sensors inside. You can see here the mess of cables, analyzing how the satellite was behaving itself. And so just with the ambient to hot curve, we were able to characterize our thermal model to a certain extent. Obviously not being able to go into negative temperatures, we had that limitation, but it was still enough for our purposes and for the satellite. And let me see what this picture is. Oh, this is a deployment test of the satellite. So this is a very critical part. Unfortunately, this failed in space. We weren't able to deploy our antenna and solar panels. I'll explain this further on. But we're using an SMD resistor and a fishing line, a Dyneema line, around the panels, which flips open the panel, which are spring-loaded, and then deploys an antenna, which is held within those panels. And it's a very cool setup. It's a shame that we didn't get it to work, and we have a pretty good prediction on why that is, unfortunately, due to a bit of a design error which was overseen. And before we go into the final results of the satellite, once it's been launched into space. We also developed some other things while we were developing FOSSAT-1. This is an educational kit, which we've sold to a couple schools in Spain. And it's a basic copy of the FOSSAT-1 spacecraft, including an IMU barometric sensor and a magnetometer, which allows students to get a hands-on experience with a satellite, which includes all these standard subsystems. So that's a power system, EPS system, OBC, a transceiver, and a set of sensors. And we actually manufactured around 10 or 20 of these, and we're still manufacturing them. They're on our web, and we make custom orders if anyone is interested. And then we also developed some custom receivers. So these have an LCD screen, and they're able to receive and transmit to the satellite and send messages within the network, and then upload them to the internet using an ESP32. Initially, we were selling these on our website. Actually, we're still selling these on our website. However, with the final launch preparations, we decided to manufacture around 20 of these and send them around for free to different individuals around the world, which would be able to establish the network of ground stations for receiving LoRa. And to date, we have around 300 stations capable of receiving LoRa all over the world. So we haven't been able to use it properly for FOSSAT-1. However, we got them ready for our next mission, FOSSAT-1B and FOSSAT-2. And we also have an educational outreach mission with giving classes at universities and at schools and getting students involved in the project. That's quite important to us. FOSSA Systems stands for Free Open Source Software and Aerospace Systems. So we're quite committed to open source development and getting all this information about picosatellites outside. And in fact, even though we operate as a commercial company, and we have contracts with other agencies and with other companies, everything we do is still open source, and our funding goes towards these satellites for an open source and a public purpose. So yeah, as I was saying, we have a GitHub. Everything is online. All our information is online, and you can access all our hardware and software for your own use. And so once the satellite was made, we had to carry it to integration. I've got a funny story. So you can imagine, at the time I'm 16 years old, I'm carrying a Pelican case through the airport, which says critical space hardware, beware. And obviously I get stopped at security, and I get brought into a white room, and they start asking me, like, what do you mean? You're a student, you're 16 years old, and you're launching a satellite into space, and you have a box which I can't open or pass through the X-ray scanner? So in the end, it all worked out. We had all the proper documentation to be able to justify the transport from the university. But it's definitely a fun experience going through security and getting people with weird looks as to why you're carrying a satellite when you're 16 years old. And so here's the satellite integrated inside the AlbaPod with its companions Trissy, Smog1, and ATL. And here's very happy me holding the backup flight model and the closed flight model inside the pod. And so launched on the Electron from Rocket Labs on the 6th of December. We had a couple delays due to a failure with the umbilical connection, but in the end, we got a proper launch and perfect orbital injection. And now this was the moment of truth, getting the first packets from FOSSAT-1. And initially we were a bit disconcerted because we weren't getting packets on the SatNOGS stations, which we had programmed observations for. And then around 3 hours after launch, we got our first packet from an Australian station, which we were actually able to partially decode. And at that moment, we were already, in the sky, happy with what we had accomplished. Just getting one packet from the project was a full accomplishment. Besides just getting it to space was already something huge, but getting data from it was the next level. And here you can see some amateur packets which we were able to decode in the coming days. Now, one problem we had is the packets were extremely weak. So we were only able to decode packets which were received with something like a 15 or 16 plus element Yagi. And initially, we thought this was a failure with maybe the transceiver, which was transmitting at a lower power. But after further examination of the radar cross section and of the characteristics of the RF transmissions, we were able to determine that the problem was actually the solar panels. So the solar panels had not opened, and the antenna had not deployed. So we weren't able to get the maximum performance out of the satellites. This doesn't mean the satellite wasn't working. We were still getting packets every day. However, we had a very reduced power budget since we had, about half of our total solar panels deployed, and we had a very reduced link budget, which only allowed really big stations to receive from the satellite. And that meant that our grid, our net of satellites wasn't able to, ground stations, wasn't able to make a full use of Pulsar-Sat 1. And that was regarding RTTY. RTTY is a very, very strong modulation, narrowband, which allows you to receive it using very old, even Soviet-era equipment. However, what we're testing here was LoRa. And the first packets we received were actually received on ground stations which had, huge Yagi antennas, recorded using the SDR. And since these people didn't have LoRa transceivers available, a bit of a logistical problem and couldn't get those transceivers to them in time, what we did was replay the satellite using an SDR and then decode it using hardware. This is because there's not an actual GNU radio decoder for your SDR, so we had to use hardware to decode from the satellite. It's a very janky setup, satellite to SDR, that packet then sent to someone on the other end of the world, and then that person retransmits it on an SDR and decodes it on an actual hardware LoRa hardware chip. So this was already a huge success for us, getting LoRa to be decoded, and we actually managed to do this thanks to Daniela Esteves, Echo Alpha for Golf Papa Zulu, which help us identify these LoRa signals. So you can just see here the up chirps and the down chirps. And then we actually managed to get a packet using hardware, thanks to Yankee Lima 3 Charlie Tango, which decoded a packet using an SX1276. So the satellite was meant to have cross-compatibility with every LoRa transceiver. However, there was a mistake in the programming of the sync word, and it only worked with SX1268 chips. But we're not sure exactly how this happened. It must have been, a lot of luck, to be honest. This normally does not occur, at least in our testing. But he managed to decode an actual packet from the satellite using his SX1276 and a huge array of 4 22-element Yagis used for moon scattering. And so at that point, we had demonstrated LoRa, unfortunately, not exactly how we wanted using antennas, very small antennas, but still, if you consider that the link budget's reduced due to the antenna and you carry out the calculations, the system worked as intended. And we weren't able to validate the solar panels and the antenna. However, we validated every other system. So that includes the EPS, the OBC, the thermal model, the passive attitude control model. We were able to, check the fading, check the rotation of the satellite using the fading in the signal. And one thing which saved the mission was RTTY. So with ground stations which didn't have huge antennas, which were able to decode RTTY using something like FLDG or MMTTY, we had to decode it by hand. And this is where the magic of RTTY comes in. It's also a huge pain, but you can decode the individual bits and then translate them to ITA2 messages. And this allowed us to get probably around 20 or 30 packets of Pulsar-Sat 1, which gave us a lot of information using stations which didn't have huge antennas. So for sure, I think including legacy modulations is a very interesting thing for allowing amateurs to get involved too. And so here are some of the mission's results. We're still evaluating a lot of these. However, as you can see here, we've got voltages. On the solar panels, as you can see, the voltages are very reduced compared to what we were expecting. We had the problem with the solar panels, and so we have a much reduced power generation. And then with regards to the temperatures, this is also an interesting thing which we got a lot of data out of. The analysis was carried out by Radiant Systems, which did a full thermal analysis on the satellite before we launched. And as you can see, all our temperatures are within the predicted and environmental margin range. So we were very happy with that. Radiant Systems were also very happy. This was their first mission, and they managed to successfully validate their thermal model. As you can see, the temperatures, at least for a battery, were always above 0 degrees, and the external temperature oscillated between -20 and 40 degrees. The battery maintained these temperatures thanks to its position touching the transceiver, which allowed it to dissipate the transceiver's heat into the battery. So now this is Fossat-1. Fossat-1 was last heard, I believe, in February. So it had a total operational life of around 2.5 months, and this is mainly due to the EPS. In fact, the satellite lived longer. The problem is it went into low power mode and could only be decoded using LoRa, since it doesn't transmit RTTY in low power mode. So in total, the satellite lived for maybe 3 months in total if you account for the time it was in low power mode, and we got something like maybe 40 packets in total, or 50 packets in total of the satellite, which isn't a lot, but allowed us to get a lot of science done on the satellite data. We've been able to analyze a lot of things, and we've been able to learn a lot, not only on the satellite data, but on the whole process of launching into space. So I'm running a bit out of time, so I'm just going to scoot over this very fast. Our next mission is the Pico bus, launching on the Firefly Alpha. So last year we made a proposal to launch on a Firefly rocket. We actually made the proposal on behalf of Fossa Systems to launch a constellation of 8 Fossasat-1s. However, we decided to take on a collaborative mission with LibreSpace and AMSAT. So LibreSpace were in charge of making the deployer. We were in charge of all the administration with Firefly and obviously procuring the launch. And then AMSAT, we gave them a free launch on this mission in exchange for them allowing us to fly a payload on their satellites. And the payload which we're using, I'll explain a bit later on. It's a pulsed plasma ion thruster biapplied ion system, but that was what they flew on the mission in exchange for them flying on this deployer. So as you can see, it's a full aluminum deployer. It's not very efficient. It weighs around 4 kilograms, but since we had a lot of up mass on this mission, it wasn't a big issue, and we got it developed in a record time of a couple of months and tested in a very short record time. TVAC and vibration testing was done in record time. And in total, from when the mission was first designed to when we got all of these satellites made, so all these satellites in this picture, from idea to launch is going to be around 1 year, and from idea to flight models is around 4 months. So it was a very, very fast development time. It's been a very stressful mission, but we've got a lot of good things out of it. And as you can see here, we've got Fossasat-1 and Fossasat-2. Fossasat-1B, sorry, which is the next iteration of Fossasat-1. And the main difference is we're using a different separation mechanism. So we've ditched the deployable solar panels, and we've decided to use actual through-hole resistors. The problem with Fossasat-1 is that the dynamo wire slipped on the resistor. So we would actually not be in contact with that, and we think that's the problem. It must have slipped off the resistor and not get activated once in space. We've still got hope that maybe the dynamo wire degrades with radiation and opens up, but most likely what will occur is it'll burn up in the coming months. But for the next satellites, we were using through-hole resistors. So we've added a lot of improvements on Fossasat-2. It's a 2P form factor. We've got GNSS capability, which we've been working with the ESA Galileo Science Office. So we have a GNSS receiver. We've got a full magnetoker ADCS. This is actually the biggest feat on this satellite. It's very complicated getting ADCS on any satellite, let alone a 2P satellite. And we're actually in the final process of testing it with the air bearing and the Helmholtz cage. However, it's fairly complete, and we're able to get full capability regarding solar tracking. So actually, in this picture, you can see we have sun sensors, so we're able to determine our attitude with regards to the sun. And we've got the panels acting also as close sun sensors, which allow us to get a reference point. And we've got an IMU, magnetometer, accelerometer, and gyroscope, which gives us all the good information for pointing our satellite in space. So we can do maneuvers, tracking, we can do nadir pointing, we can do sun tracking. It's just quite complex, and it's been very complicated to develop. By far, one of the hardest things we've done. And that was with the local university and another association which we're developing with them. And we're flying an OV2640 2-megapixel camera, which gets us a resolution of around 100 meters per pixel. We have store and forward capability. We're using external memory, 512 megabytes. We have a new OBC architecture, so we're using an STM32, which gives us much improved performance and much improved capability. Here we have the ADCS systems with the H-bridge and the IMU, and we have a no connector system using these pogo pins, which are spring-loaded. So we learned from Fossat-1, and this satellite has no cables at all. So the panels just sandwich, and the satellite just works without any sort of cables. And here we can see Fossat-2 with the GPS antenna, with the resistors, and our IXYS cells. So we've really optimized the last space. We've got 4 panels on each side, and then the camera, light sensors, temperature sensors, and the back panel. And here's Fossat-1B, also a similar system. It's the same as Fossat-1, but with the different panels, a couple electrical fixes, and no deployable solar panels. And now the payload we're flying on the Genesis N and L are the Applied Ion Systems pulsed plasma thrusters. So we're testing with these to be able to do basic maneuvering in orbit. For now, it's just going to be basic firing to be able to evaluate orbital raising maneuvers. However, since the thrust created by these thrusters is so small, for now, we think this is only going to be able to be used for attitude control systems. However, it's still a very interesting thing we're doing, and we hope to be able to fly Michael's thrusters in the future. He's got several iterations using other sorts of propulsion systems which aren't only pulsed plasma thrusters. So we'll see how this works out in space. You can see here the Genesis satellite and the Cubic satellite in the deployer. And well, I mean, this is pretty much the end of the presentation. This slide is just a bit of an idea on what could happen in the future. For now, this constellation in space at the time of launch is going to be 2 or 3 satellites. But who knows, maybe in the future, we could be launching several more satellites communicating between themselves. One thing I haven't mentioned is Fossat-1B and Fossat-2 have an inter-satellite link. So that's also something which we want to demonstrate. And see how these satellites could be used in the future for IoT communications or demonstrating other sorts of technologies. So our website, last thing, with the COVID crisis, since the university's closed, we've had to work from home. And so here's an ISO 7 approximately. Well, the filter is ISO 5, but I suspect it's an ISO 7. It's a clean room I made at home to be able to work on the satellites. So this is what we do to be able to work when the coronavirus crisis closes your facilities. This is literally 5 meters away from me. And yeah, so you can check our website out. We have a full explanation on our satellites, and we have some other pictures which you can take a look at. It's fossa.systems. We also have a shop on here, and you can see exactly what we're doing. So I think we'll go into the questions. If that's okay, I'll just answer the questions which have been left in the chat. Yeah?
Yeah, that's fine. So thank you for such an informative session, Julian. It was really informative. So we have a question from participants. So it's by Soumitra De from Santini Lab, and the question is,
Yep.
how did you increase the range of DRF-126 at T up to 300 plus kilometers from space? Is there any amplifier to increase the range?
Okay, so one common misconception we have with LoRa is that it can only be used for 20 or 30 kilometers in terrestrial range through buildings. That's more or less what people think. When you tell them that you can establish a 1,000 kilometer link with a common $3 chip, most people won't believe you. The trick is using a very, very low data rate. We're not using any amplifiers. It's literally the output from the DRF chip, and using this large bandwidth and high coding rates. So the link budget's very simple to calculate for yourself. It's literally just down to the low data rate. If you go up to higher data rates, like 25 kilobytes per second, then obviously you're only going to be able to reach maybe 5 kilometers. But at these low data rates, there's no problem in achieving these huge distances. And the next question is, on the solar panel, will it be a wise idea if we deploy the panel using a command from ground, like you have the fossil ground station with SX1268 and ESP32? Well, the one thing I would recommend is not depending on the on commands from space. So one possibility is that your satellite will not have its antenna deployed, and so that means that there would be no way of getting commands up to the satellite. The best thing is to have a timer. In our case, we had a 30-minute timer, which would open up the satellite after deployment, and it would then repeat the loop every couple of orbits to make sure that the satellite has opened its panels. Will you be selling your ground station in your online shop, or will you publish what equipment we need to buy to build one? Well, all the information is online. You can check our GitHub. We sell them on our shop. If you're interested, you can contact us. However, we encourage people to build them themselves. It's very simple using eBay parts. And we have a full guide on the FossilSat-1 GitHub. So if you search up FossilSat-1 GitHub, you can actually, even easier, groundstationdatabase.com. So the link is groundstationdatabase.com. And in here, we have a full guide on how you can communicate with the satellites. This is for FossilSat-1. However, it's nearly identical for FossilSat-1B and FossilSat-2. And this explains everything in detail. And the last question, do you know when the next satellites will be launched? Right now, due to the COVID crisis, we've had a bit of delays. However, we're considering, or at least we've been told by Firefly that the launch will occur in late July to August. So by then we should be in orbit.
Okay, so I have one more question, like what kind of legal procedure did you follow to transport your satellite? So while transporting your satellite, so what kind of legal procedure you did?
Okay, so typically transporting something through well, first of all, before getting into what exactly we did, so we transported the satellite through air as a carry-on using a Pelican case. If I just go back to that slide there, so we just had a Pelican case with our flight models, and typically you wouldn't have any issues traveling with this through airport security. If you just pass it through your X-ray machines, no one will say anything. There's no problem. The issue is we didn't want to corrupt or have any bit flips on the satellite. You pass your computer through X-ray machines every day, but we just didn't want to take the chances on FossilSat-1. So what we did was prepare documentation from the university and arrange with the local airport to be able to not have to pass the Pelican case through the X-ray machine. The problem is we can't open the case or the bag where the satellite is concealed because it's in a clean room environment. We couldn't show the satellite to them. So one thing we had to do is prepare some documentation from the university, legally certifying that it was a project for investigation, that it was a satellite, and that we weren't lying, and get it signed off by the department director at the university. But for that, it was fairly straightforward.
Okay, so one more question, like what made you, what was your reason behind selecting SMD resistor over THD resistor in your previous FossilSat-1 for thermal life?
You refer to the SMD resistor for burning the wire,
Yeah, for the thermal life, yeah.
Okay, so the problem, I mean, to be honest, looking at it now, it wasn't a good decision since we have very reduced surface area on the SMD resistor. The main issue was space. If we put a two-hole resistor, we would go outside of the envelope. So we didn't have enough space for a full resistor. That's why I had to go for the SMD one. Looking at it now, I don't recommend using an SMD resistor in any case. Please use a through-hole resistor. You can actually see the on Phosphosat 2. We're using two through-hole resistors, so it's a redundant system. It loops around, and it really assures that we won't have any sorts of issues with the satellite. So really, it was a bit of a design flaw, and looking at it now, it wasn't really justifiable.
Okay, so one more question, like how difficult was it for you to coordinate the frequency for LoRa mission?
Getting the frequency permission you're referring
Yeah,
to?
yeah, exactly. For our frequency for LoRa mission especially.
Yeah. So the IRU initially denied our application. They were very skeptical about LoRa because it uses a large bandwidth and they think no one can decode it. So they thought we were a company which was using LoRa for in an encrypted manner for communication within our own network. That's obviously not the case, and dozens of amateurs have participated in the missions and have a LoRa transceiver. However, the IRU are very old-fashioned, and if you don't have pen and paper to decode a modulation, then they're most likely not going to accept your modulation. In the end, we managed to convince them. We had to report a brief document explaining why we wanted to use LoRa and how it fit into the amateur community. But it was definitely quite complex. And I recommend if you do use LoRa, which isn't the best modulation, I'm going to say that straight away now. There's better modulations, and in fact on Phosphosat 2, LoRa is a secondary modulation. We're now using JFSK as our primary modulation. Then I recommend getting all your licensing done way before time when you've done your preliminary design review.
Okay, so like in your Photosat 2, like you have used GFSK for the image, right? Not the LoRa. Okay.
Yes, we're transmitting JFSK at 9.6 kilobytes per second.
Okay. I think that's all the question I have. Jitin or Rakesh, any questions?
Yes. I'm just checking the pictures, and in the Genesis, I can see there are two antennas. Is it because of two different frequencies, or what is it?
So the Genesis satellite is a regenerative transponder. So they have uplink on UHF and downlink on VHF. So they have two antennas which sort of stretch out of the sides. In our case, we have uplink and downlink on UHF. So that's why we have only one antenna, a dipole, and they have two monopoles.
Okay, yeah. And about the image taking, like, did you do this calculation for the amount of data that you need to downlink, and how many, maybe in how many passes can you downlink one picture? Some numbers.
So if I recall correctly, I think one image is like 200 kilobits. We do quite a bit of compression on it, and we can downlink. I think I don't have the exact numbers. It depends on the quality at which you downlink it, but I think probably 2 or 3 images per pass is what we can achieve.
Okay.
And we can also store the images on the memory. So we can take a picture and then downlink it at a later time.
Okay. And do you also consider the packet loss? Like, what will you do if there is a packet loss?
Yeah, so there's error correction in the packets, and you're able to request lost packets. So obviously the packets are divided in dozens for an image, and if a packet is not received correctly, then you can re-request it again.
Okay, nice. And based on your experience, like you already launched your satellite Pocket Cube, what kind of you would not do, or what kind of lesson learned, maybe in points?
Okay, so there's a lot of lessons learned, a lot, like
Yeah,
really,
if
to
you
anyone
like, you
out
can list
there,
them in the points. Yeah.
to anyone out there, I think there's no better way to learn about space than to actually launch a satellite. Getting a first-hand experience is the best way to learn about it. The first thing is satellite legislation is very complicated, and launching a satellite into space is very bureaucratically intensive. And I had to learn that the bad way. It took me like 1 year to get the licenses for the satellite. I have a guide on the GitHub if anyone is interested, but it's very complicated to get it done the first time. Thankfully, in Spain, it's not too bad, but it definitely takes some time. Then the second thing is, for your first satellite, keep it as simple as possible. It's better to have a successful first mission, which is simple, than a brick in space. It really is. There's no point in launching if you're not going to be able to get it to work. In our case, we kept it simple. We had some problems, but the mission worked out. We got data. We're very happy with it. And now, which we've learned so much from the first mission, keep in mind, even keeping it that simple, we learned a lot of things. We've advanced to the next iteration. And then my last tip is going to be testing. Testing is very important. There's nothing as simple as testing. The relationship should be 20% manufacturing, 80% testing. It's all testing, in my opinion.
Great. Thank you.
Great. Then if there's no questions.
Is there any questions, Julian? I think there is no more questions, I guess. So yeah, thank
Okay,
you very
well,
much, Julian. Thank you very much for such an informative presentation. We look forward to collaborating in future. Yeah, we are still collaborating, but then we look forward to collaborate more in future.
on my end, thank you so much for giving me the opportunity to talk here. It's really an honor. Like I really thank you guys for organizing this conference. It's great to be able to participate in this webinar now with all the coronavirus situation. Being able to do this from my house is definitely cool. And as you say, I really look forward to working more with you guys in the future. And for anyone else which has any questions, just drop us an email. We're very open. If you have anything you need help with, then within our time and our capability, we'll try and reply.
Yeah, and best of luck for next mission.
Thank you very much. We'll keep everyone updated on our Twitter.
Sure. Yeah, okay. So